Good morning, everybody. Thank you for coming. I'm excited to be here at the Databricks Spark Summit EU. It's great that you found your way to this presentation. When I submitted the abstract for this talk, I was worried if this is something that people would interest, scaling SparkR in production. And if you think this is not an issue for a speaker, you might be wrong. I just spoken recently to a leading AI researcher who told me that he had previously, just in summertime, he had given a talk. And when he came into the room, there was just a single person, the one person there, a lady sitting in the first row. So that was sort of the worst, sort of a nightmare for a speaker. But he was quite gracious. He gave the talk nonetheless. He came up to the podium, started the talk, and told her he's happy to give the talk for her, and he's welcoming her, and so on. And she dryly replied, "Thank you very much, but please hurry up. I'm the next speaker." So in that case, we're quite safe now. Hope people enjoy this presentation. Who am I? Couple of words about myself, but not too much. Heiko, Korndorf, my name. I'm a founder of a small startup company called Wireframe, doing Spark consulting services, Hadoop consulting services, and we're about to launch a Spark IDE for rapid application development quite soon. That was my little plug here. Other than that, I'm a Master of Science in Computer Science. I'm mentioning that because that gives you the idea, or gives you information. I'm coming in from the data engineering side of things. We're going to talk about this data engineering, data science for a bit during this talk. My background in the last 20-odd years, not so much web stuff, obviously, was more classic enterprise stuff, ERP, CRM, BI, EAI, and cross-industry, number of industries. So that's a couple of words. And got into Hadoop and Spark actually 3-4 years ago, and was was infected by this enthusiasm by this community, and was just not quite sure would this catch on in Europe, but here we are today, and we all agree that this is something that is here to stay. What is this talk about? Data science challenge, classification of this talk. It's something, it will contain something of everything. It will talk mostly about, faithful to the title, scaling SparkR, but it's also about, for data engineers who are wondering how they could integrate data science applications in their production pipeline, and potentially about, for management people, if there's anybody in the audience, what challenges could arise from managing integrated data science, data engineering projects. I'd like to quickly just have a show of hands to give me an idea who I'm talking to in these three categories. Who is a data scientist in the audience, who's familiar with Spark, with R, and is sort of, that's his or her background? Okay. Data engineering, people who are, okay, so it's roughly 50-50. Any managers in the room? Okay. And since I'm coming from the engineering side, I'm learning the ropes of the data science business, and I'm told I have to understand my population in entirety. The invisible fourth category, anybody in here who is not a data scientist, doesn't know about Spark, doesn't know R, doesn't manage any project, has nothing to do with scaling SparkR in the remote sense? Good, good. I'm fine, we're fine, we have the right audience here. Good. The agenda, what we're going to talk about. This talk is inspired by two projects. They're different industries and quite differently set up, but we found it interesting that they showed the very same characteristics. I'll show you in a minute, the next slide, what that is. But they showed the same problems, and then we thought, like, this looks like a pattern that might be more broadly applicable and apply to many more situations. Basically, they are both our applications in production, but having trouble with scaling and performance and so on. And in both cases, we were looking at SparkR, how to scale it with SparkR. And this talk is maybe not necessarily a finished textbook case study that will give you the end result and say, this is what all worked. This is literally a journey, and we're in the middle of the journey. I can give you some, hopefully, insightful data about what we've achieved so far. But clearly in the future, there's work left ahead and stuff to be done. So we're going to see about that, and that's a journey for some of you who might be interested to have who will have embark on the same journey, and maybe we can then join forces and learn from this together. And in the end, we'll talk a bit about briefly about what I mentioned, integrating data science and data engineering, and have a broader look at the ecosystem as well. And outlook and next steps, obviously, is the last slide. Data science with R, I'm not talking much about this because I suppose those who are concerned know about R. Just recap, it's a very popular language. I think there's Python is the other pillar of the machine learning community, but R is really obviously a strong element. Many people have a background in R and are very happy with the language. It was designed by statisticians. Yesterday, Ali Zaidi from Microsoft gave a talk about Microsoft's HD Insight-based version of Spark and R, and funny enough, he said one of the pros of R is it was designed by statisticians. One of the cons of R, it was designed by statisticians. That gives you and tells you a lot about the language. So it has some advantages due to that fact, but it's also limited by that fact. There's a large community, and one thing that always gets mentioned, I'm not quite sure what to make of it, to be honest. Being an R outsider in a way, I started R a year ago, 1.5 years ago, is that you always keep hearing that there are thousands of packages. I'm not quite sure how to heavily you have to weigh this argument, but clearly the general takeaway is, of course, it's powerful, it's functionally very rich. There is something in it for everybody and every problem, more or less. But we'll see how this is a factor to consider going forward. But of course, what's the problem with R? That's perfectly fine for prototyping, for small data sets, but as we talk about big data, scaling R, that's a challenge. And SparkR, or R is limited, is usually a single server solution, which means data has to fit in memory. It's very memory-centric. And there are ways to exploit parallelism for R, but it's limited. I'm not an expert on that, but we'll talk about this also in a couple of slides. So these are the problems that you usually would have when you work with R. Now, real-life projects, and we will refer to those two examples. They're quite similar. Obviously they have on the left-hand side, they have data sources. The upper project, data is coming in from mainframe systems and not necessarily data warehouses and other legacy systems. Data is exported in CSV files and then processed by R script, which in turn spits out CSV files as results and also graphics, PNG files. And the second project is data is already in Hadoop. This is exported from Hadoop onto a CSV, not distributed file system, processed by R, again produces CSV output, and then again fed back and uploaded into distributed storage and further processed downstream. Both projects challenging. In terms of performance, the project above, the first one, runtime of the R script around about 20 odd hours. Project number 2, multi-day, up to multi-day runtime, so not really ideal for production environments, and the idea was how can we shorten this with SparkR. Given that in project 2, Hadoop already was installed in the landscape. In project 1, there was a Hadoop cluster just about to be inserted into the landscape and about to go live. So that was a natural choice to also look in both cases. How could we use SparkR for this, to deal with this? By the way, there's another problem, as you can see, obviously. There's not only the scaling is a problem, but data integration was a problem. In both cases, data export, reading in, then feeding it back, and providing it to the downstream systems is clearly a challenge. And we're also trying to tackle that with SparkR. But one step at a time, the first thing was performance. 1.5 years ago, one of the first interesting insights was, what is SparkR? Because the data scientists, being very well versed in R and all these methods, but not necessarily familiar with Spark, they were not quite clear what this SparkR now is. And truth to be told, it was the same on our side from the Spark and engineering side. Things like, we knew Spark quite well, but SparkR seemed like another library, but what would it exactly do? So from an R perspective, it seems like it's just a package that you import. It's the SparkR package, and that gives you another API, another set of APIs that you can use, and it opens up the door. On the right-hand side, you could see the Spark, obviously, but also Hadoop and NoSQL database and other data sources. So it would open up the world, the door to this wonderful new world of big data. But it was clear, obviously, to everybody involved that this is not going to solve the problem. We're not going to be able to just move and migrate the existing R code over to SparkR and run it on SparkR and problem solved. But rather, how can we exploit the capabilities of Spark? And that means mostly parallelizing, exploiting the hardware resources that we have available on the cluster. If you look at SparkR from maybe a slightly bit more from the data engineering side of things, in that perspective, this slide will give you a rough idea how the SparkR architecture looks like. At the very center, you see this big box with the shaded background, and this is this would be the R driver. That's the application, the central application that Spark is running. When Spark is launched, it will then instantiate an R process and give control to the R process and execute your script. So far, that's the same thing as running it on a single server, with a difference that, of course, it could run on any node in your cluster. It's a trivial thing, by the way, but we'll see in the next slide, or the following slides, that we exploited this small thing, and already this very trivial way of doing things enabled us to reap quite substantial benefits. But more on that in a second. So technically, if you run now that, what can you do with it? You see on the bottom of this slide, you see UDFs, HBase. HBase is a representative of NoSQL database. It could be other stores as well. And on top, you see this bar, Spark data frame, and this is the key abstraction. Spark has an abstraction called Spark data frame, and it was named deliberately data frame on purpose to be as similar to R as possible. So it should be, it should give people sort of a familiar environment, but it's a different object, obviously. So if you're in your R shell and you have access to a Spark data frame, you cannot invoke the same functions on the Spark data frame as you would have with a local R data frame. It's a different thing. The advantage is what actually it happens is this is not on your local machine or on the machine where your driver is running, but the data frame in Spark is, as all those Spark people would know, obviously, is distributed. So it's actually a logical data frame that physically is located on a number of nodes across the cluster. The advantage of that, no more limitations in terms of data size. So your data frame can be arbitrarily large. And that's an interesting thing, obviously. But still, if you want to do then classic computation in R, most libraries work with R data frames. You have to collect them, which means, collect is the API, which means you have to materialize them on the single node. And this is where things get then tricky. That was the main feature. There's other things, but the main feature for Spark are in Spark 1.x. Spark 2.x brought user-defined functions, and that's what I try to sort of visualize with the R boxes on top. That allows now this driver R script that you have to execute R functions on your nodes. So that will allow you to parallelize your computation. And we're going to see how this plays out. We used all these things in both projects. For simplicity, I'm using the first project. This is the only data science slide here that I'm using, which is a time series forecasting project. Not going much into this. Just a private remark here is that time series is something I was familiar with before big data came, and when I grew more accustomed to the ecosystem, I saw the AI and ML activity going on, but I'm still puzzled that it seems, relatively to speaking, to classification and clustering and regression and all the areas that you currently have, time series is I'm not sure if you can call it a stepchild. It's interesting because I think there is a huge demand for that. People are obviously wondering what will happen in the future. They want to forecast and predict the future, and time series is one set of tools you can do that with. But moving on, what is this time series? The actual algorithm that's used in the project one is far more complicated, and it's some also proprietary stuff in there. But there is a set of methods, and we'll choose one of it, which is called ARIMA, and I think most people here in the room are probably familiar at least with the term, some might be familiar with the algorithm. Basically is trying to forecast a time series, obviously. And a time series is a set of, the definition would say, data points indexed in time order. And ARIMA is an established method, I would say, mid-90s. It was the consensus that this would be a useful method to predict time series data. It would have basically an autoregressive part, which would try to predict the future on a regression, autoregressive, which means with a lagged version of the time series. There is a difference. There is a differencing where you difference your time series observations, and there is a moving average part which tries to predict the forecast future observations or future data points with a moving average approach. And ARIMA is the name, the combination of that. We're skipping the details, obviously we could spend a long time on that, but the interesting thing is, as you can see, there are 3 parameters in ARIMA we determine your model, P, D, and Q, which are the order of the autoregressive part, the degree of the first differencing, and the order of the moving average part. What this means is, with the order of the autoregressive part, you can choose how long back you take your regression with which you use it to forecast it. Now, this gives you, in terms of computational sense, a large search space, and you can do a lot of parallel models and try and see and fit how each model would work out for you. And this is what Project One did. They did, on a given time series, work out and compute thousands of models, actually, and then do a number of tests to determine which ones would be the ones best suited, and then in a second stage still then select another subset of that, and then come up with what they believe will be the optimal prediction. How could we parallelize that? Well, that was obvious that this was something we could parallelize, but the problem was, and we'll see this will come back and remain a constant challenge still, is we actually have 2 layers of parallelization. We have one layer is the individual time series, where we have thousands of models that we compute, with each one in turn thousands of computations. And we have not only one, but we have roughly 1,000 time series in turn to predict. So how could we do this? And that was spring of this year, we used Spark1.x for that. And this is what we came up with, what you see here on this slide. And it's actually a trivial approach, but very useful. And we'll see in the next slide what the results were of that. Is what we did is just literally split up the whole computation, and we let every single time series run as one R script and run on one node. The difference was, previously the data science team had used a server, and they had actually invested significantly into a single server that they would use. But as we know, scale up with a single server is very limited. But what we had an on-prem cluster with 100 nodes. So that gives you a lot of hardware power. And what we then did is obviously say, like, look, you have 1,000 time series. Well, you can calculate obviously 10 time series on that node, and 10 on that node, and 10 on that node. That will give you already quite a significant degree of parallelism, time saving. And that turned out to be true. Why SparkR? We did not use very much of SparkR in that scenario. What we did use actually is a combination of Yarn and SparkR. We wrote a little Java client that submits these jobs to the Yarn cluster. And Yarn, Hadoop/Yarn, then selects a suitable node for that and executes that script. And that script then runs on that node, still sequentially doing all those thousands of models. Data was materialized from, we did use a little something which it's still doubtful if it's the best thing we could have done. What we did, we materialized data from UDFs directly onto the node as a yarn dependency, not via a Spark data frame. The reason, because our data frames or the time series were quite small. We're not talking big data. We have years and we have monthly aggregations, so you can think we have 50, 100 data points maybe, so it's very, very limited. So for that, to instantiate a separate data frame, a SparkR DD or a data frame on your node, was deemed maybe too expensive, so it was just the cheapest way, materialize that little CSV file down to the single node and let the execution and the computation run. Results of that, as I said, despite a very straightforward and not overly sophisticated approach, very helpful, very, very useful. The sequential computation on a single server was more than 20 hours, close to a day, and that was with the initial set of time series. It was bound to grow, and it is bound to grow. It will grow even more significantly in the future. There were attempts to parallelize it on a single server, bringing it down. I think it was also a quad-core machine, or maybe 6 or 7 8-core machine, to roughly 4.5, 5 hours. But since we had this cluster available, what we did is, even on a modest cluster with 25 nodes and quad-core nodes, we could bring it down to 12 minutes. And that was very, very helpful and regarded as a success story and gave us great confidence to go further and do more. I'm going to talk about what we're going to do more in the future now, in the next minutes. Quickly, what these numbers mean, it's quite straightforward, actually. This is literally embarrassingly parallel parallelization, which means 12 minutes, actually, is roughly the longest calculation of a single time series. Time series forecasting, in this case, varies because time series have different characteristics, and the algorithm that they used is looking at that is as a stationary time series. It has some trends, it has seasonal effects, and so on. Depending on those characteristics, the models that we're trying to build were more or less sophisticated, and it could be, let's say, a very constant time series could then be computed in literally seconds, whereas time series exhibiting more complicated patterns would take up to 12 minutes. That was more or less the longest running time series, which was in this setup also the sort of the maximum time or the minimum time that we could reach with this approach to parallelize it. It also adds quite nicely up. We have 25 nodes, 4 cores, which means a degree of 100 parallel computations that we could run, and 100 times 12 minutes equals roughly about 20-something hours. So that all adds up quite nicely. The work, what's been done, Yarn was doing sort of the cluster management, and that worked quite nicely. We had this, as I said, this Java client that just submitted hundreds of jobs, and we used that to make management easier of that procedure, so you could see which jobs were still running, etc. It's a little mini console. You could see that through Yarn as well, to the resource manager console, but it's not really built for that and meant for that. Yeah, and SparkR in that sense was used as a bridge between the Hadoop world and executing an R script. And this will grow now in the future with a new functionality that's been added to it. One small thing, I'm going to very briefly touch on this. This is a nuisance, nothing theoretical, nothing that will give you food for thought from a data science perspective, but has to be done, is we had this on-prem cluster. And for SparkR, you have to have R installed locally on your cluster. And that was not the case for various reasons. I'm not going to go into any detail. That was just no way currently or quickly in short term we could install R on that cluster. So what we have to do, it's open source after all, and that was from an engineering perspective, the fun part, where to tweak R and Spark and make R dynamically deployable, which was a bit harder than we thought it would be, because if you install R locally on your Linux server or on your machine, actually the installation path is hard-coded in R, which is a bit of a nuisance. So we had to tweak that and tweak both Spark and R and bundle that, which allowed us to then dynamically deploy R on the cluster. This is an exception, and probably few people will run into this problem because most will have R installed. Just mentioning it, it might be beneficial. One thing is it would allow you to run multiple versions of R in parallel. We didn't find this to be an issue because it seems people are fine with R 3.2x or 8.3 latest version or even some older version, there doesn't seem to be a large degree of dependency on the specific R version. But what it might be prove to be useful in the future is if you have an on-premise cluster, you might have some problem with outside connectivity. And as we know, data scientists are very prolific in using one of those 10,000 R packages. And the R installation mechanism makes it easy to download and install a new package, which might not be possible in an on-prem cluster. So this solution was easy because that would allow us to just literally for every run include the new packages as the data science needs would evolve. The next step was then we moved on for various reasons, moved on from the on-prem cluster. There were some discussions and issues around this. And then we had the chance to move to Microsoft HD Insight, Microsoft's Hadoop Spark cluster on the Azure cloud. And that worked quite nicely. That was summertime. That worked quite nicely. And we did the same approach, but we got rid of this Java client, which was an extra bag of carriage that we had. We replaced it with the user-defined functions that Microsoft offers for that. But it is not SparkR. It uses Spark as a cluster distribution mechanism, but the interface between Spark and R is Microsoft's approach based on the Revolution Analytics acquisition that Microsoft made last year. That worked quite nicely. I'm not going to go into much detail. We don't have much time left. There was a talk from Ali Zaidi from Microsoft yesterday telling much more about HD Insight, so I can encourage you to have a look at that talk once it's released on the web, which will tell you more about this. But that's the state that we were in, and the runtime was approximately the same. The difference was, as I said, data integration was here a much easier thing. And then that was summer, briefly before Spark 2.x was released, and once it was released, I think it was August, we moved to Spark 2.x, and that now offered user-defined functions. And now we could do what we had done previously outside the cluster, inside, meaning we could parallelize inside the cluster, have one R script run, and that in turn would spawn a number of child processes doing computation. What does SparkR 2.x bring or give you? Basically, there are three APIs. It's called in tendency to be similar to the R ecosystem. It's dapply, gapply, and SparkLapply. Dapply gives you parallelization for each Spark partition. Gapply gives you a way to arbitrarily group data set, a data frame, and then run a computation per group. And SparkLapply is actually, we're not quite sure what's the benefit there is giving you just parameters. All the examples there are based on built-in R data sets, so that might be an issue for that API. We're using gapply, group apply, which gives us the ability to parallelize per group and finally control the parallelization, degree of parallelization for that. So that's very nice. This is where we currently are, and now going forward, we say it's scaling R. People are wondering, well, every data scientist you talk to is clear. Cluster gives you hardware benefits, but equally, the first thing that people then think of, well, there's a limit to what you can do with your algorithm. The algorithm is limited in terms of its parallelization, and that is obviously true. Spark gives you a very powerful model for that, in memory and iterative, but essentially in terms of parallelization, it is still map reduce. You have a map and a reduce step, and you can iterate over that in memory. That's all good and fine, but going forward in the future, there are algorithms that cannot be necessarily parallelized in such a trivial way. You will need a more generic approach. Now, a fully generic approach is probably maybe not an elusive goal, but clearly a more ambitious goal. But there are things you can do in between, as I just said before. And we're looking now at combinations going forward, which is, one thing is sort of a two-level parallelization. One thing is to have, if you have loosely coupled sort of computation, you can have a client sitting outside the cluster and use the cluster as such to parallelize your application. Then you can have each Spark application can again use UDFs and parallelize internally. That would give you that. The other thing we're currently looking at is obviously GPUs are very big, and we're hoping that this would be another breakthrough because, as I said, we have thousands of models per time series that we're running. So the ambitious expectation would be that we would bring down those 12 minutes we talked about, potentially even to seconds. So that would be our ultimate limit that we could hit on that. I'm running short on time. Just very quickly, cultural integration. I'm not going to go into stereotypes, but it was funny to see how those really played out, that you have these ingrained differences, and not necessarily problematic, but it's good to be aware of them and to just really sort of be clear how to deal with them and going forward. Spark ecosystem. On the slides you'll see when you look it up, there is an ecosystem. Other things are interesting as well in the ecosystem. We looked at all of them, didn't fit our needs, so we had to move on. And the last thing is Outlook, as I said, simplification of data integration, data pipelines, and GPU calculation. That's going to be our clearly focus for the next step, and hope to bring in more performance improvements. So that was my talk. Thank you very much for your attention. Questions you have? I'm over time, yes. So I'm taking questions if you have any after the talk. Brian, over to you. Thanks.